All right, we're going to do an application of vectors, a very, very classic one. So we have a weight of 100 pounds. So go down, and we have an object, and we got 1,000 pounds. By the way, this point is going to be the origin. So the horizontal, which is the positive x-axis, will be there. We're going to assume we have a two-dimensional space. And this weight is going to be supported by two cables. One cable, so this is 100 pounds. One cable will be 45 degrees off the horizontal, 45 degrees. And another cable will go 30 degrees off the horizontal the other way. So that's, assume that is 30 degrees. Assume we have a tension down of 100 pounds. The question is, what is the tension on each one of those cables? And what are those vectors, the vectors that represent those tensions? We're going to label this as tension 1 and this as tension 2. And again, the origin will be where the three cables join. It is important to realize in this example that the length of the cables is irrelevant as far as the 100 pounds go. Of course, if you have a lot of cable, then you are adding weight to the 100 pounds. So it is not 100% irrelevant. We're assuming the cables are weightless. Otherwise, we have to take into account the weight of the cables themselves, or the rope or chain or whatever we're using. But we want to think of the tensions. We want to find the tensions regardless of the actual weight on the cables, because again, I'm just repeating myself, the cables could add weight forces, and but we're assuming there is no mass, there's no weight force to the actual cable itself. Anyway, so let's assume that T1 has coordinates. So T1 is a vector, and it has coordinates A, comma, B, two-dimensional. T2, we're going to assume it has coordinates C, D. And of course, this other vector that goes down will have coordinates 0, comma, negative 100. We can break T2 into two vectors. Well, the C coordinate is the same as the vector. Well, I shouldn't say, I cannot compare a coordinate with a vector. What I mean by that, what I was saying is that this length is the first coordinate, or it could be thought of as the vector C, comma, 0. And then we can go up 0, comma, D, and so we can break this into two vectors. Or we can just think of them as the coordinates. So the coordinate here is C, coordinate there is D. Similarly here to the left, this is A, and that would be B. So A is pointing to the left, B is pointing up, C is pointing to the right, D is pointing up, and then we have this pointing down. All right. If we know the magnitude is the same as the length of this, then since we have the angle, we can write A in terms of the magnitude and 30. Before I do that, though, let me start out with an initial equation. So the initial equation that we're going to use is this. Tension 1, the vector tension 1 plus tension 2 plus this third vector, 0, comma, negative 100, will be the vector 0. Remember, this could be a little bit confusing, but it shouldn't be because of the context. In fact, that could be a little confusing. A lot of people put arrows but I'm not. So this is vector tension 1, vector tension 2, plus this vector is going to give us the vector 0, 0. If you want to put arrows to emphasize that we have vectors, that is okay. And in fact, a lot of people would say that is very good. So what we are saying is that A, B plus C, D plus 0, comma, negative 100 is equal to 0, 0. Now it is more clear that we have an equation of vectors. And we add vectors component-wise, which means that A plus C plus 0 is equal to 0, or A plus C, well, let's write it down, plus 0 equals 0, while B plus D plus negative 100, B plus D plus negative 100 is also equal to 0. So the initial setup uses vectors, but we can break the vector equation into two equations or a system of equations. A, by the way, will be the magnitude of T1 times, by trigonometry, we will have the cosine. A represents the horizontal, A represents the horizontal distance. So A will be the cosine of 150 degrees. Notice that if this is the origin and this direction is the positive x-axis, then the angle starting here and going out to T1 is 150 degrees. So cosine 150 degrees. B will be the magnitude of T1 times the sine of 150 degrees. T1 times the sine of 150 degrees. C will be a magnitude of T2 times the cosine of 45 degrees. I'm going to put parentheses on the trigonometric functions. And D will be T2, the magnitude of T2, times the sine of 45 degrees. Of course, this is magnitude of T1 times square root of 3/2 of negative, which makes sense that we have a negative number there because A goes into the negative direction. And that's why we want to use 150 degrees rather than 30 degrees, because otherwise we would not capture the fact that we are going left. B is the magnitude of T1 times the sine of 150 degrees, that is a half. Yep. And these are easy, those are the same. Magnitude of T2 square root of 2/2, and magnitude of T2, and again, square root of 2/2. I'm putting parentheses to indicate that we're multiplying those two quantities. So now this system of equations, let's go back to the system of equations. There it is. Let me put a symbol there indicating that we have a system of equations. A plus C equals 0, and B plus D equals 100. If we move the 100 over to this side, we'll translate into a system of equations using T's, T1 and T2. So let's do that on the next page. So A plus C will translate into T1, negative square root of 3/2 magnitude of T1, plus C square root of 2 over 2 plus square root of 2 over 2 magnitude of T2 equal to 0. And then we have B, which is a half of T1 plus square root of 2 over 2 T2 equals 100. Remember, the 100 initially was negative when we were adding B plus D plus negative 100, but then we moved the 100 to the other side of the equation. If we subtract one equation from the other, so there's our system of equations. If we subtract the second equation minus the first equation, then the second term will simplify, will add up to 0 if we subtract. So we end up with T1, a half minus the negative. Again, a half minus the negative, which means we're really going to be adding if we subtract the second equation minus the first equation. So, and we're going to have T1, magnitude of T1 rather, times a half plus the square root of 3 over 2. Remember, the reason for that is because we are double negative. We have a double negative there, equals 100. So we can multiply by 2 to have 200, and then we can divide by the quantity of 1 plus the square root of 3. So the magnitude of T1, T1 is equal to 200 divided by 1 plus the square root of 3. So again, we multiply by 2 to get rid of the 2's here, and then with those two are going to end up being 1 plus the square root of 3, which then we divide, and then we get the magnitude of T1. I made the numbers beforehand, and I got about 73.2 pounds. 73.2, so that is about 73.2 pounds. Yeah. So that is how much this cable is tensioning by about 73 pounds this way. Now, if we were naive, we would think, oh, if this is 73 and this is 100, that means this should be the complement, so 27 pounds or so. Well, that is not true because this setup is inefficient. If we were holding this with just one rope vertically, then yes, 100 pounds up and 100 pounds down from this point. But we are not doing that. We are actually, we want the sum of this to be 0. So there's different kinds of tensions going on because of the angles. The angles are making this system inefficient. And consequently, there's tension here and tension there, which add up to more than 100. So far, we got about 73 pounds of tension on the rope on the left. Now, once we have T1, we could find T2, but instead, I'm going to take the system, multiply the second equation by square root of 3, and then go from there. And then we're going to use the elimination method. So if we take the second equation and multiply it by the square root of 3, the entire equation, we end up with square root of 3 over 2 times the magnitude of T1 plus the square root of 6 over 2 magnitude, I missed to put down magnitude here, magnitude of T2, close the magnitude, equals square root of 3 times 100. Let me double check. So we multiply this by the square root of 3, multiply this by the square root of 3, and multiply that by the square root of 3. And so we have a new equation, which we can subtract. Again, this equation from the new equation. So actually, no, we want to add the two equations to eliminate the magnitude of the first tension. Yeah. So if we add those two together, we eliminate the magnitude of tension 1, and then we end up with square root of 2 over 2 plus square root of 6 over 2, both multiplied by the second tension, the magnitude of the second tension, and then square root of 3 times 100. So let's write that down. We have the square root of 2 over 2 plus square root of 6 over 2 multiplied by magnitude of second tension equals the square root of 3 times 100. And just as before, we can multiply by 2, getting 200, and divide by the square root of 2 plus the square root of 6. So the magnitude of the second tension will be square root of 3 times 200 divided by square root of 2 plus square root of 6 pounds. Before I put down the pounds, let me figure out how much that is on a calculator. I made the numbers earlier. It is about 89.7 pounds. So let's not put the equal, sorry to show you this scratch. 89.7 pounds. So the tension on the second cable is that much, close to 90 pounds plus 73 pounds. So of course the total is somewhere in the neighborhood of 160 pounds. And that's how much those two cables together are holding. Of course, the reason is because the system is inefficient. Even though we have only 100 pounds going down, the two together are pulling against each other, and that adds to the poundage, to the weight, to the forces. Again, because of the inefficiency. They're pulling away from each other, and that's why we have that. So those are the tensions, the magnitudes of the tensions. Oftentimes, we want to know the actual vectors. But now that we have this, it is easier to figure out the actual vectors. Let's go back to this sheet where A, so let me take this off the table for the view. So A is equal to magnitude of T1. I'm copying this from the previous computations, times negative square root of 3 over 2. But we just found the magnitude of T1 to be 200 over 1 plus the square root of 3. 200 times 1 plus the square root of 3 times negative square root of 3 over 2. So the 2's cancel, simplified. 200 divided by 2 is 100. The square root of 3 cancels. I'm just joking. Of course, the square root of 3's don't cancel because this is a term, and terms don't simplify across fractions. Factors do, but not. So here we have 2 times 100, and that simplifies with the 2, but not the square root of 3's. Of course, you knew that, but it doesn't hurt to overemphasize it. So we end up with negative square root of 3 200 times, oh, wait a minute, 100, because remember, let me write it underneath. Sorry about that again. This is square root of 3, 100 over 1 plus the square root of 3. And that's it. Oh, no, there's a negative because A goes to the left. So negative square root of 3 times 100, because the 2's simplify, 1 plus the square root of 3 stays in the denominator, so we're good. B is first tension times what we obtained by, I have to redo this. No, I'm good. The first tension multiplied by a, now I have to look at what B is on my sheet, 1/2, and that is 200 over 1 plus the square root of 3 as before, but this time we multiply it by 1/2, and that leaves us with 100 over 1 plus the square root of 3. So the tension 1 vector has components: A, negative square root of 3 times 100 over 1 plus the square root of 3, B, 100 over 1 plus the square root of 3. As you can see, this 1 plus the square root of 3 is repetitive as a factor, so we can factor that out and makes notation a little neater. Oftentimes it is desirable to do that. In fact, the 100 can factor out too. So we end up with 100 over 1 plus the square root of 3. And then we have a nice vector, square root of 3, comma 1. And that gives us a nice direction. A nice direction. This makes sense. This should be familiar to you. We know this has to do with, there's a negative missing here. This has to do with 30 degree, 60 degree, 90 degree triangle. Those are some of the sides of that kind of triangle, which makes sense because in our original picture, we did have a right triangle with a 30 degree angle in it. So this is 60 degrees. All right. I'm gonna let you figure out T2. Make sure you simplify and you obtain the exact answer. And with that, we're gonna stop this video.